Alright, welcome to my AP Physics 1 Semester 1 review, where we will be covering 4 major units: kinematics, forces, centripetal motion, and energy. So let's get right into it with kinematics. So I'll just show you my basic thought process for the majority of kinematic questions. So usually what I like to try and do is put everything into a velocity graph, right? So with a velocity graph, let's say I have something like this. Alright, and now let's label this as like 2. I'm just generating a random value. T equals 2 seconds, and it travels until it has, let's say, 5 meters per second of velocity. Now, from here, we can calculate just about everything. We can calculate the acceleration, we can calculate the velocity, obviously, and we can calculate the position or displacement from this. So, in order to calculate all 3 of them, let's take a look at position. So if we want to calculate the position from this graph, what you want to do is take the area under this curve right here. You want to take the area of that. Now, as you can see, it is a triangle, and in order to take the area of a triangle, you want to do base, right, which is 2 times height, which is 5, and then you want to divide that by 2. You can cancel this out, you get 5 meters per second, 5 meters traveled. And if you want to find the total, the acceleration throughout this region, then you have to do the slope, which is rise over run. So in this case, our rise is 5 meters, right? 5 minus 0 over our change in time, which is 2 minus 0, right? Your run. So your rise is 5, your run is 2, which gives you an acceleration of 2.5 meters per second squared. Alright, now let's get into the actual questions. So let's look at the first question. Section 5 of the velocity versus time graph. The object is speeding up, slowing down, and in which direction? So what I like to do if they're asking me if it's speeding up or slowing down is use this sort of chart right here. Alright, so we're going to take the slope of the velocity, and we're going to take the actual value of the velocity. Alright, now I'm just going to label the signs. So you only really need to take a look at the signs. If the signs are the same, and excuse me for my poor handwriting on this app, still getting used to it. The signs are the same, that means the object is speeding up. And vice versa, if the signs are different, then the object slows down. Alright, so in section 5, right, which is this area over here, you're trying to find if it is speeding up or slowing down. So let's take a look at the slope of the velocity. Now the slope is positive, right? From a visualist perspective, it is going up. So it's going to be one of these two right here. And we're going to see what the actual velocity is. So the velocity here is negative because the velocity, right, the graph is still below the x-axis. So we're going to have this one, meaning that the signs are different, so the object is slowing down. And then we can cancel C and A. Now we need to determine if it is moving in the positive or negative direction. For that, all you have to do is look at if the object is moving, or if the object's velocity is positive or negative. So as we found out here the velocity is negative, so you will be slowing down and moving in the negative direction, and that corresponds to choice D. Now for number 2, a baseball is thrown straight upward. What is the ball's acceleration at its highest point? So with this, the only force that is acting upon the ball is gravity. Okay, so your acceleration will be just g. There's no other force acting upon it, so it'll only be g. Now we can cancel out a and c from that, and we're trying to find out if it is upward or downward. Well, because the ball is thrown straight upward, we're assuming that the gravity is pulling it toward the center of the earth, where in this case it would be downward, right? Because if you throw a ball up, it will come back down, right? So you would choose B for this one. Now, how long would it take a car starting from rest and accelerating uniformly in a straight line at 5 meters per second squared? How long would it take that car to cover a distance of 200 meters? We can use a velocity graph for this question. All right, so starting from rest means that the initial velocity at t is equal to 0 is going to be equal to 0. And now we're trying to find a t value so that if you accelerate at 5 meters per second squared, it will cover 200 meters. Now, if we want to find this value over here, the final value, all we have to do is set your rise, which is going to be your y value over here, over t equal to 5, right? Or actually, I'll label this v, not y. So v over t is going to be equal to 5. So by that, you can just isolate your v. You get v is equal to 5t. Now we can replace this v with 5t. So we get 5t over here. Now, in order to find the distance traveled, you have to take the area under the curve. And now we have to set that area under the curve, right? 5t times t over 2 because we're working with the triangle again. Set that equal to 200. Then we get 5t squared is equal to 400. T squared is going to be equal to 80, and the closest perfect square to 80 is 81. So square root of 81 is 9, so your answer is going to be approximately 9 seconds, and that does correspond with an answer A. Alright, now a rock is dropped off a cliff and strikes the impact velocity with an impact velocity of 30 meters per second. So we can use another velocity graph for this question over here. Now, when you see dropped off, you're assuming that the initial velocity is equal to 0. Once again, so now the only force acting upon it is gravity, and we're assuming that gravity is equal to 10 meters per second squared. Sorry, negative 10 meters per second squared. And with an impact velocity of 30 meters per second, okay, because this is positive, we're assuming that the positive direction is actually downward. So we'll actually have that as 10 meters per second squared. So we're going to set this equal to 30. Now we want to find the displacement, right? So in order for that, what we can do is set your rise of 30 over your run, set that equal to t, equal to 10, right? Now you can make 30 equal to 10t. T is going to be equal to 3, right? So we can replace this t with 3. Now we can find the displacement of this using a triangle. So we get 3 times 30 over 2, and then we can cancel that to get 15. You would get 45 meters of displacement, and that is equal to your actual height of the cliff. All right, so 45 meters, and that corresponds with choice C. All right, now let's move on to question number 5. Oh, right, I forgot to label it. Yeah, it's C, right? Okay, so let's look at number 5. It's stone horizontally with an initial speed of 10 meters per second from a bridge, and assuming that air resistance is negligible, how long will it take the stone to strike the water 80 meters below the bridge? All right, so Just draw a diagram real quick. This is your stone. The stone horizontally, and will go somewhat like that. All right, so what we want to look at, because you're trying to find how long it will take to strike 80 meters below the bridge, you're only going to be looking at the vertical velocity. And because it is thrown horizontally, there is no initial vertical velocity, right? So we can create another velocity graph starting at the origin, because once again, the initial velocity is equal to 0. And because the only vertical force acting upon it is gravity, right? You got to remember that motion in the x is independent of motion in the y, or in this case, motion in the horizontal axis is independent of motion in the vertical axis. The only force acting upon the stone vertically is gravity, which is going to accelerate the stone at a rate of 10 meters per second squared. Sorry, negative 10 meters per second squared. And now you're trying to find the time t it takes to go 80 meters below. So because the slope is equal to 10, you have your t here. This velocity over here will be 10t because rise over run, right? You'll have, so that's supposed to be negative 10t, sorry. But you'll have your final velocity, right, over t is going to be equal to negative 10. Then v, your final velocity is going to be equal to negative 10t. So you will have negative 10t times t over 2, because we're working with a triangle. It's going to be equal to 80. Sorry, negative 80. So then you get negative 10 t squared is equal to 160 if we isolate the t's. Sorry, if we move 2 to the other side, now we'll isolate the t's. T squared would be equal to 16, thereby making t equal to 4 if we take the square root, and that corresponds to choice C. Now let's move on to question 6. Right, a soccer ball at rest on the ground is kicked with an initial velocity of 10 meters per second at a launch angle of 30 degrees. Now we have to calculate its total flight time, assuming that air resistance is negligible. Now total flight time is only determined by a vertical motion, right? Because if a ball is kicked like this, the horizontal motion doesn't really affect how long it takes to go up and back down. So now we need to find the vertical component of the velocity, right? So now we know that the total initial velocity is 10 meters per second, right? And we have 30 degrees here. So now we're trying to find what this velocity is, right? What the upper velocity is. So with that, we can just use trigonometry, and you have sine 30, right? Your opposite over your hypotenuse, your opposite from 30 is going to be your vertical component. And if you do sine of 30, that's going to be equal to 0.5, right? And then you multiply that by 10. So you get 5 meters per second in the vertical direction. Now, you can still use a velocity graph for this, right? So if you have that trajectory, your ball is kicked upward at 5 meters per second, and it will come down backward at 5 meters per second. So if we were to draw a velocity graph, you have it at 5 meters per second here, your initial, and your final will be negative 5, because it is coming downward at negative 5 meters per second. So now the only force acting on it from a vertical perspective is going to be gravity, which accelerates the ball at negative 10 meters per second squared. So our slope is going to be equal to negative 10, right? Now from that, we can use our rise over run. So your rise is going to be equal to negative 5 minus 5 over t, which would be equal to negative 10. So then you can simplify that to equal negative 10 over t is equal to negative 10. Your t would then be equal to 1. And if you look at it like this, right, you'll find out that it reaches the top, right? Because it's a parabola, the time it takes to reach the top and the time it takes to go back down are equal, so this part is symmetric. And if that is symmetric, the integral, or the area under this curve, and the area here, they're equal but in opposite directions, meaning that the change in x, right, or sorry, the change in y, the displacement vertically, is going to end up being 0. So we can conclude that 6 is equal to 1 second, right? All right, now let's take a look at number 7. Okay, so a stone is thrown horizontally with an initial speed of 30 meters per second from a bridge. All right, so we have a stone thrown like that, and it enters the water 4 seconds later. Okay, so we're trying to find the total speed, right? Which would be equal to your, let's just draw this real quick, right? It will be equal to the horizontal speed and the vertical speed. So you're going to have to use the Pythagorean theorem. Right, now your horizontal speed will remain at 30 meters per second because we are assuming that air resistance is negligible. So with that, 30 meters per second will remain constant because there's no other force acting upon it. Right, there's no acceleration, there's no deceleration. So this will be equal to 30. Now we want to find the vertical speed. All right, now because the ball is thrown horizontally, we are assuming that there is no initial vertical velocity, and we can once again use a velocity graph. So because our time is equal to 4, and we're accelerating at 10 meters per second squared again, sorry, negative 10 meters per second squared again, our rise over our run, right, we'll label this v final, our final velocity. So v final over 4, your rise, right, over your run is going to be equal to negative 10. And then we can isolate your v final to get negative 40. And that will be your final vertical velocity. So now we plug that in here, and then use Pythagorean theorem. So you get 30 squared plus 40 squared. And the reason I'm using positive 40 squared is because they're asking for speed and not velocity. So then you get 30 squared plus 40 squared. Square root of that should be equal to 50, right? And that should be your answer, C. All right, now which of the following, actually I don't need to screenshot this. Which of the following statements is true concerning the motion of an ideal projectile launched at an angle of 45 degrees to the horizontal? All right, actually I might need to screenshot this, sorry. All right, so with this, your diagram should look something like that, right? This should be what your trajectory should look roughly about, right? Should look something like this. So now let's read option A. The acceleration vector points opposite to the velocity vector on the way up and in the same direction as the velocity vector on the way down. So your acceleration vector is gravity, which points straight downward, but your initial vertical vector, your initial velocity vector is going to be heading this way, right? Which is not the opposite direction here, and it comes down this way, which is not on the same, not the same exact direction. So you will have to cancel A out. Now the speed at the top of the trajectory is 0. Now this initially does sort of look right for the vertical component. The vertical component is 0 at the top, right? Over here, it is basically at rest from a vertical perspective, but you have to take into account that you are launching it at an angle of 45 degrees to the horizontal. So meaning that you do have a horizontal non-zero component and you have a vertical non-zero component. So you have to take that horizontal component into account. So there is still speed at the top of the trajectory. Now, the object's total speed remains constant throughout the entire flight. That is also incorrect because your horizontal component, once again, does remain the same, but your vertical component decreases, right? Your vertical velocity decreases at -10 meters per second squared, so this is incorrect. Now, your vertical speed decreases on the way up. Yes, that is true, right? If we were to draw a velocity graph, we'll have something like this for our um, vertical motion. And on the way up, we can use that chart we used in the first question again. On the way up, the velocity is negative, but the actual velocity itself is positive, right? The slope of the velocity is negative. So meaning that if the signs are different, the speed is decreasing, it is slowing down, but after it goes on the way down, the velocity itself is negative and the slope is negative. The signs are the same, so it is speeding up, and that matches with our D. Now let's take a look at number 9. So a stone is thrown vertically upward with an initial speed of 5 meters per second. What is the velocity of the stone 3 seconds later? So because it is thrown vertically upward, we don't have to worry about horizontal velocity, right? And if we are throwing it vertically upward, our only force against it is gravity, right? Which once again accelerates at -10 meters per second squared. So we have our time of 3. Now we gotta find this, right? So basically we can set our rise over run equal to -10, right? So your V final minus 5 over 3 minus 0. We set that equal to -10, right? You multiply 3 to this side, you get V final minus 5 is going to be equal to -30. Then you separate the V final, you get -25 meters per second. And that corresponds to answer B because in this case the negative signifies that the object is going to be going downward. Alright, so we check B. Now a car that is traveling at speed of V initial applies its brakes, getting to a stop over a distance of X meters. Alright, this is interesting. Now assuming that the deceleration due to the brakes is constant, what would be the skidding distance of the same car if it were traveling with twice the initial speed? Alright, so let's just label this as V initial. It takes about T time. T1 is our own variable that we are creating over here. Right, so this area, right? So now we'll label V initial times T1 over 2, that we label that as equal to X. And we also have to label the slope of this equal to A. Alright, so in this case our slope would be negative V initial over T1, right? Because our rise is negative V initial, it goes downward over T1. We set that equal to A. Now let's draw another one with the initial velocity being twice of the original. So we put that at 2 times V initial. And then we set this equal to T2. Now we're going to solve for T2. So we're going to have that, right? And now we can, because we know that the deceleration is constant, you're going to have -2 V initial over T2 is going to be equal to A. So, right, your T2 is that. So because A is constant throughout these two equations, you can set them equal to each other. And with this, now you can take out the V initial from both sides. So now you get, and you can also take out the negatives. So now you get 2 over T2 is going to be equal to 1 over T1. You can cross multiply. So you would get T2 is going to be equal to 2 times T1. Alright, so now we can replace this T2 with a 2 times T1. Alright, so now with that, we can find the area under both curves, right? So we already found this, the area under this curve over here is going to be equal to V initial times T1 over 2, which is we're setting to X. And now we're going to use another one. We're going to find the area under this curve over here, which would be 2 times V initial times 2 times T1 over 2, and that would be equal to 2 times V initial T1. We're going to set that equal to Y. Now we want to find the proportion between Y and X. So from there, we can use this over here, 2V initial T1 over V initial T1 divided by 2. As you can see, you can cancel out the V initial T1s to get 2 over 1 half. And you would get 4, which is going to be equal to Y over X. So basically, if you were to cross multiply that, your Y would be equal to 4x, and your Y is basically your area under here. So because of that, now we know our distance traveled is 4x. We can check that. Now let's submit to see if we're all right. And everything is right. Now let's move on to our next unit, forces. Alright, now let's get started with the forces unit. So let's take a look at the first question. Alright, so a person standing on a horizontal floor feels 2 forces, the downward pull of gravity. Let's just draw this free body diagram, downward force of gravity, mg, and the upward supporting force from the floor, or in other words, the normal force. Now these 2 forces, alright, so because we are assuming that the person is standing still, right, in static equilibrium, we are assuming that the normal force is equal to your mg, so that he's still, right? So he's not accelerating in either direction. There's no net force on him. So therefore we can cancel out C and D by that. Now we have to determine if this is a an action-reaction pair or not. So basically what an action-reaction pair is it's based off of Newton's third law. So every action, right, has equal and opposite reaction. So let's say you got a person, right, pushing a box with a force of 15 newtons. The box pushes back at him with another force of 15 newtons. Right, so I guess if an object exerts a force on another object, the object that is receiving that force also exerts a force back onto that person or that other object. So in this case, right, gravity is exerting the force on the person. The reaction force for this would not be normal force, it would be the person's gravitational pull on the earth, right? So we got the earth here, pretty small earth, but the force of gravity is mg. That's what the earth is doing to him or her, but that's what the force of gravity is doing to the person. Now, the reaction force would not be normal force. It would be the person's pull of gravity on the earth, right? So mg that way. That would be the reaction force, not normal force. Normal force is something completely different. So they do not form an action-reaction pair. It is B, our answer. All right, now let's take a look at number 2. A person who weighs 800 newtons, right? So when I see weighs 800 newtons, I'm thinking that mg is equal to 800, right? Because F is equal to ma. right? That's basically the premise of this entire unit. F is equal to ma, and in this case, a would be g, right? The value of your acceleration would be the gravity downwards. So in this case, g is supposed to be equal to 10. So we got 10m is going to be equal to 800. And then we can conclude that m is going to be equal to 80 kilograms. And now we're trying to find what the normal force is, because what will the scale read? The scale reads the normal force. So if we have a man on an elevator, right? Now we got to find the force of the elevator upward. Now, the elevator is supposed to be going downward at 10 meters per second squared, assuming there is no force from the elevator. But we have we have a force of the elevator going upward, and that makes the net acceleration equal to 5 meters per second, right? So we'll do acceleration of elevator minus 10 meters per second squared, because we're accelerating upward and gravity is headed downward, so we have to subtract the gravity. And we got to set that equal to 5 meters per second squared. So then we can conclude that the acceleration of the elevator upward, the force would result in 15 meters per second squared. Right, that's the acceleration of the elevator. That's not the net force. That's like the force that's applied by the elevator should lead to that, but gravity takes away from it. So then from there we can conclude, we can use mass times acceleration, your acceleration being 15 and your mass being what we solved here as 80, right? Because you're trying to find that, right? Now the person's inertia, right, Newton's first law, he wants to stay still. This person wants to stay at 0 meters per second squared, but they're now being pushed down onto the elevator at 15 meters per second squared. You can think about it like that. So then we can use F is equal to ma, where we're trying to find the F, and we're given we found out m and a. So then we can just multiply this and we get 1200 newtons, which corresponds to choice D. Now let's take a look at number 3. Alright, a frictionless inclined plane of length 20 has a maximum vertical height of 5 meters, and an object of 2 kilograms is placed on the plane. So 2 kilograms. And now, when they say the length of the inclined plane is 20, they're talking about this length right here. That is equal to 20. And the vertical height is 5. So from here, I'm not going to go too far in depth about why this is your formula. But we know that the acceleration down a ramp, down an inclined plane, is going to be g sine theta. So we can multiply m by that to get our force, right? Mass times acceleration is equal to your force. So n times g sine theta, right, is equal to your F. And because that is your only force, the only force is gravity on this, unaffected gravity on this, and because that is your only force, this will be your net force as well. So we know that the mass is 2 kilograms, and we know that gravity is 10. So F is going to be that times sine of theta. Now, this is our theta over here. We do not need to solve for it. We just need to know the proportion, right? So the opposite over hypotenuse is equal to 0.25. So we can just multiply 0.25 right here, right? And actually we'll replace this sine theta by 0.25. So we'll have 2 times 10 times 0.25, or over 4. So you would get force is equal to 20 over 4, which you can then simplify to 5 newtons. And that is A. Let's take a look at number 4. Alright, so a 20 Newton block is being pushed across a horizontal table by an 18 Newton force. Now, when you see 20 Newton block, that is implying that it weighs 20 Newtons. So we can use mg is going to be equal to 20, 10 m, right? You replace the g with 10, it's going to be equal to 20. Your m is going to be equal to 2 kilograms. Okay, and we know that because this is a horizontal table, we don't need to worry about cosine or all those trigonometric functions. So we have that, and we have our coefficient of kinetic friction equaling 0.4. So the force of kinetic friction is equal to mu times mg. We know that mg is equal to 20 from here, so we can use 0.4 times 20, and that is equal to 8 newtons. So our kinetic friction's force is going to be equal to 8 newtons. And we know that this is our force that the 8 newtons will act against. So we'll have to go 18 minus 8 because the friction acts directly against this force. That gives us a net force of 10 newtons. Now with 10 newtons, we can set that force equal to mass times acceleration, where we figured out that the mass is going to be equal to 2. And now we just separate the a and you get 5 meters per second squared, which corresponds to choice C. So now we're going to input C for number 5, and now we'll do, number 4, and now we'll do number 5. Alright, so we are given this equation, this question. So coefficient of static friction between a box and a ramp is 0.5, and the ramp's incline is 30 degrees. So if a box is placed rest on top of the ramp, the box will do which of the following? Alright, so we have this, we have a box, right? So it is inclined at 30 degrees from the horizontal. Now, what we can do is we have to set the coefficient of static friction, the force of static friction, which in this case, once again, I'm not going to go too far in depth into why, but we have, this is our formula for, because mg cosine theta is your normal force, right, on top of a ramp, and now we want to multiply that normal force by mu, and that gives us, or actually we won't write whether that's greater than or equal to or less than. We want to find that out, and we want to set this to mg sine theta, right? Because that is our weight, or that is our gravity, that is our pull from gravity downward, and our static friction is acting upward. Now we want to find if this right here is greater than, equal to, or less than this side of the equation, right? We want to find if this is equal to that, or greater than or less than whatever. So we can cancel out the mg's, so we get mu times cosine theta versus just sine of theta. Now we can use trigonometry here, and if this is a special right triangle, so we get root 3 over 2 for cosine of 30 times mu, which is equal to 1 over 2, right? 0.5 is equal to 1 over 2, and we have to set that equal, we have to determine if that's equal to, less than, or greater than sine of 30, which is equal to 1/2. Right, so now we get, alright, so with this we can just cancel out the 1/2, right? So we get root 3 over 2 versus just 1, and we can use a calculator for this one. So root 3 over 2, it is less than 1, right? As you can see here, it is less than 1. So now we know that because your force of statics, your force your applied force, right, your downward force, not applied, your gravity, exceeds the maximum amount of static friction possible. Now, if that happens, you turn into kinetic friction, and that's another entire concept. But now we know that it is moving down the ramp, so we can cancel out d. And so usually, no, not usually, all the time, static friction, your coefficient of static friction, is going to be greater than that of kinetic friction. And because your force of gravity is greater than static friction, it's always going to be greater than your kinetic friction force. And then that would mean that you have a non-zero net force working down the ramp. So it is not with constant velocity. Now accelerate briefly down the ramp, but then slow down and stop. There is no opposing force that comes here as far as we know. So we can cancel this out. And we do know that it does accelerate down the ramp, so A is our answer. Now let's take a look at question 6. I'll just take 2 screenshots. This question's pretty tall. It's given a diagram and everything. Alright, so we can do that. We shrink that. Alright, so with this, assuming a frictionless, massless pulley, determine the acceleration of the blocks once they're released from rest. Alright, so we can use that, and we know that acceleration is now, if we isolate it, is equal to F over m. Alright, so first let's take a look at the m of this total system. The total mass of this system is going to be equal to your block 1 plus the friction of your the mass of your pulley, right, which is 0 because it is a massless pulley, plus your mass over here, right? So in our denominator we have m plus m, big M plus little m. So that is equal to that. Now we have to find the force, okay? Now we're assuming that the positive direction is whatever is happening on the right side of the pulley, downward. And the negative direction is what's happening on the left side of the pulley, downward. Now on the right side of the pulley, the force pulling downward is big mg, right? That's going to be positive big mg because it is in the positive direction that we established. And on this side, we're going to have little mg, a negative little mg because that is in the negative direction that we established. So that will be our force, our net force. And we have that. Now we can take the g's out of this equation, so we get g times big M minus little m over big M plus little m. And from this we can see that corresponds to D, which is our correct answer. Alright, now if all the forces, actually this is more of a conceptual question, I will not need to screenshot. So if all the forces acting on an object balance out so that the net force is 0, then the object, so actually I guess I could use it a bit, but we have this. So if your net force is equal to 0, you're setting this equal to 0. You're setting your mass times acceleration equal to 0, your non-zero mass. So you can't cancel the mass out. Or actually, you can cancel the mass out. You get zeros over m is going to be equal to a, meaning that a is going to be equal to 0. Your acceleration is 0. So if your acceleration is 0, that does not mean that your object's speed will decrease. That means you have a negative acceleration. And the object's direction of motion can change, but not its speed. No. Acceleration does take direction of motion into account, and you will see that in centripetal motion. Now, the object must be at rest. It does not have to be at rest. An object could be moving at a constant velocity of 5 meters per second, and that means that it still does have no net force acting upon it. and it would have 0 acceleration. So it doesn't have to be at rest. So our choice should be D. Now, a block of mass m is at rest on a frictionless surface, and you will be testing what it is like on the moon versus what it is on the Earth. So if you read this question, we have a block here on Earth and a block here on the moon. Now we'll just label them mass m because they are both the same. Now we are pushing it horizontally, right? We're pushing it across the table horizontally, and the only forces that change on moon and Earth are gravity and your normal force, which are completely independent of what is happening in the horizontal axis. So this changes, but your horizontal forces do not change at all. So in order to accelerate at the same rate, the forces should remain the same. And because it is frictionless, right, so the normal force does not really matter. It does not really affect this system because it is frictionless. If there was friction, you would probably end up with a different answer. All right, now let's move on to number 9. All right, let's screenshot number 9. So we have a crate of mass 100 kilograms at rest on a horizontal floor. And so we have our floor. So a force of magnitude 344 newtons is applied here. Now we have this static friction coefficient of 0.4. So because we are on a horizontal plane, our normal force, right, is going to be equal to mg, because we have mg pointing down. You should also have a normal pointing up, and there is no vertical acceleration. So you would have n is going to be equal to mg, and then you can have your mu times mg. So that would be 0.4 times 100, which is your mass, times your acceleration of gravity, that's 10. So that would be equal to 400. So because static friction is a reactionary force, it will only go the total force that is exerted. It would only, like, how do I explain this? It would only exert the same amount of force here, assuming that this force is not greater than your static friction. Your static friction. So this would not be 400, it would be 344 newtons this way, because it is a reactionary force. Now, this means that the object would still stay at rest because you're initially at rest and you do not break the you do not break it past the static friction barrier. So let's read the choices. The crate will accelerate across the floor. No, because you still have not broken the static friction barrier. Now, the static friction force, which is the reaction force to F as guaranteed by Newton's third law, will also have a magnitude of 344 newtons. Now, this does seem correct, but as we discussed earlier, the reaction force to F would not be friction, right? Because it would have to be another object applying another force onto it. So if you're applying 344 newtons this way, your reactionary force would not be on the object, it would not be from anything else other than another object. Another object would have to exert that force onto this object, right? So the reactionary force in this, right, actually, so let's say a person was pushing it at 344 newtons, the reactionary force would be the object exerting 344 newtons back at the person, right? So let's say a person is pushing it at 344 newtons. The reactionary force would be this object exerting at his hands 344 newtons. So we can conclude that friction is not the reactionary force, or not the reaction force. It is a reactionary force, but not the reaction force. So we can cross out B, and you see the crate will slide across the floor at a constant speed of 0.5. No, you have not broken the static friction barrier. Now, if this was kinetic friction and the kinetic friction force was equal to that, then that would be correct, but we are still in static friction. So it is not moving at all. We are in static equilibrium. Now the crate will not move. We did conclude that to be correct, so D is our answer. Now for number 10. So we have two crates stacked on top of each other, crate 1 and crate 2. And they are of equal mass. So both crates, yeah, so compared to the strength of force 1 necessary to push only crate 1 at a constant speed across the floor, right? Only that force applied. We have to put that at a certain force, and that would equal to a constant speed. The strength of force 2 necessary to push the stack, right? Push this pile the same speed across the floor is greater than force 1 because okay, so the only force that would be acting upon these is kinetic friction, or yes, kinetic friction, because we're pushing it at a constant speed. Now, kinetic friction is equal to your mu times your normal force. Your normal force on this is going to be equal only to mg, right? Because you're not accelerating vertically. But for this one, you're going to have 2 mg because you have 2 blocks. So your normal force onto object 1, right, your crate 1, would be 2 mg, right? So your kinetic friction force is going to be equal to 2 mg, which is greater than mg. So there will be a greater force pushing back. So the normal force on crate 1 is greater. Yes, we concluded that. Now let's just check the rest of the options. The coefficient of kinetic friction between crate 1 and the floor is greater, and the coefficient of static friction. Now, the coefficients do remain the same. The total force doesn't, but the total force varies, but the coefficient still remains the same. You have to remember that. And D, the weight of crate 1 is greater. Now, the weight of crate 1 is still going to remain at mg. It's only the normal force because we have another object, we have another crate pushing down on to crate 1, which then increases the surface contact, increasing the normal force, not the weight. So we can cross D out. And we should get everything correct. And yes, everything is indeed correct. All right, now we will get started with the work, energy, and power section of Physics 1. So we will start with question 1. A force of strength 20 newtons acts on an object of mass 3 kilograms as it moves a distance of 4 meters. Now if F is perpendicular to the 4 meter displacement, the work it does is equal to... Alright, so what they want you to do is use this formula right here, but you have to remember when using this formula, the force over here is only the component that is parallel to the distance traveled, right? So if you have an object moving here, if you have that object, right, only the force applied in this direction, only the component of the force applied in that direction is taken into account when calculating work. Now what we're assuming is that there is an object moving a certain direction, but the force that we're given is applied perpendicularly to the object's displacement. So the work, right, we have to calculate the amount of the force that is parallel to this, right? But there is no component that is parallel to it because perpendicular is the exact opposite of parallel, so the work should be equal to 0. Now, under the influence of a force, an object of mass 4 kilograms accelerates from 3 meters per second to 6 meters per second. How much work was done? All right, so as we know, the two ways to calculate work are force times distance, and the other one is change in energy. Right now, so the only energy in this system that we're given, we're assuming that it is only based off of kinetic energy, right? And we're trying to find the change in energy. So we'll label this as V1 or V initial. We'll label this as V final. Right, so now we have 1/2 m, we can factor that out. Then we get V initial squared minus V final squared. And we know that 1/2 m is going to be equal to 2, because 1 over 2 times 4, you get 2 times your V initial, which is 3. Sorry, you're supposed to do V final minus V initial, my bad. V final minus V initial. And that should be changed up here too. Right, so now you know that your V final is equal to 6 meters per second. So you're going to do 6 squared minus 3 squared. And within the parentheses, you should get 36 minus 9, which gives you 27. And then if you multiply that out, you get 54 joules. And that is your answer. Corresponds to B. Now let's take a look at number 3. The box of mass m slides down a frictionless inclined plane of length L and vertical height h. Right, so L is representing this length right here. Now we want to find the change in gravitational potential energy. Okay, so gravitational potential energy is measured just by mgh. And now you're going to look for the change in it, which while sliding down, your h becomes lower. So you will be subtracting potential energy. So you should get that, but okay, so you're trying to use force times distance for this one right here, for this equation right here, and your force is mg. Now, you're looking for the distance parallel to the force, or the force parallel to the distance. I'll show you how to do that later. You do end up with the same answer, but let's just do a distance parallel to the force. The distance parallel to gravity in this is going to be h. Now, if you're going to do it based off of distance, you would do L, right, your distance, times your force. Now your force in this would be mg sine theta. If you're going to go down the inclined plane, the force of gravity would be mg sine theta for that. But mg times sine of this theta over here, sine of this theta gives you h. So you would get, h over L, right? Opposite over hypotenuse, you would get mg h over L. These L's cancel out, so you would end up back with mgh, negative mgh, which is B. All right, now, while a person lifts a book of mass of 2 kilograms from the floor to a tabletop 1.5 meters above the floor, how much work does the gravitational force do on the book? So you do use mgh over here, and your mg is going to be equal to 2 times 10, get 20 times 1.5. So you're going to use negative mgh, right? And then you get negative 30. The reason you're going to go negative mgh is because you're trying to use your change in height, right? Force times distance. Now your change in height is going to be 0 minus 1.5. Yeah, because we're assuming that the gravity is positive. So because gravity faces down and you're lifting the book up, you're going to go negative 1.5. Or if you want your distance to be positive, then your gravity would be negative. So you'd have negative 10 as your acceleration or your gravity. Now we have negative 30 as our answer for number 4. All right, now moving on to number 5, a box of 3.5 kilograms slides down the frictionless inclined plane with the length of 6.4 meters. That makes an angle of 30 degrees with the horizontal. All right, so we have this, which is 6.4 meters, and now I'm just going to fill this in. We might not need it for this problem, but using special arc triangles, we can conclude that this side is going to be equal to 3.2. Now, if the block is released from the top of the incline, what is its speed at the bottom? So we could use force times distance for this. We could use mgh, right, where your change in h is going to be equal to 3.2. So you're going to use mg times h, which will be equal to your change in energy, your change in your mechanical energy. Sorry, not mechanical, your kinetic energy. Hold on, let me write that better. 1/2 mv final squared minus 1/2 mv initial squared. Now your v initial is equal to 0, so we can cancel this part out. So your mgh is going to be equal to 1/2 mv final squared. You can cancel out the m's. So now your g times h is going to be equal to 1/2 v squared. And now we want to separate the v's, the v final. So we get v final squared is equal to 2gh. Take the square root, your v final is equal to root 2gh. Now, your h right here, right, we figured out is going to be equal to 3.2. So we're going to go 3.2 times 10 times 2. And we're going to take the square root of that. Now, this should give you 32 times 2, so you'll have root 64, which is equal to 8. And that is your v final, which is C. Now we'll look at number 6. All right, now let's take a look at number 6. So as a block of mass m slides down an inclined plane of length s and height h, so we'll have h and s. If F is the magnitude of the force of kinetic friction acting on the block as it slides, then the kinetic energy of the block when it does reach the bottom of the incline will be equal to one of these choices. So what we could do is use the force for this, the net force. Net force is going to be equal to mg sine theta minus the kinetic friction, which is just F. Now we want to multiply this all by S. So you would get mg sine, and we're labeling this as theta. So we'll have mg sine theta times s minus fs. But remember that sine theta of s is essentially h over s times s, so the s cancels out, so you do get h. So it would be mgh minus f times s if you were to simplify. And this corresponds with choice C. Alright, now as a rock of mass 4 kilograms drops off the edge of a 40-meter high cliff, so as a rock drops off this cliff, it experiences air resistance, whose average strength during the descent is 20 newtons. At what speed will the rock hit the ground? So the average strength during the descent is 20 newtons. That means that the force pushing upward is around 20 newtons, right? So we want to calculate the net force pushing down on the rock. So we can use 40 minus 20, which should give us our net force downwards. So that would be equal to 20 newtons downward over the distance of 40 meters. So 20 times 40 would be equal to 800, which is equal to our change in velocity. Now, because your v initial is 0, you would go you would go 1/2 mv final squared minus 1/2 mv initial squared. But because v initial is equal to 0, you can cancel that out. So you can just put 1/2 mv squared here. Now that makes 1600 equal to mv squared. Then you can cancel out 4 from both sides to get 400 is equal to v squared. So your v would be equal to 20 meters per second would be your answer, which corresponds to D. Now an astronaut drops a rock from the top of a crater on the moon. When the rock is halfway down to the bottom of the crater, its speed is what fraction of its final impact speed? Alright, so we can use force times distance for this. So mgh versus 1/2 mg versus mg times 1/2 h, right? So if you were to divide those two, right, the work done halfway down the work done from the top of the crater to the bottom of the crater is equal to 2 times what it is half of the crater. So essentially you could do this 1/2 mv squared on the middle is equal to, so 2 times this is going to be equal to 1/2 mv bottom squared. So then we can take out the 1/2 m's. Actually, we can just take out the m's, and we would get v middle squared is going to be equal to 1/2 v bottom squared. And then we can conclude that, so we can move 1/2 to the other side to get 2v middle squared is equal to v bottom squared. And then we can take the square root of both sides to get root 2v middle squared, root 2 times v middle is going to be equal to v bottom. So now in terms of in terms of v bottom, or the final impact speed, you will have root 2 times v middle. And if you want to find Vm in terms of Vb, right, which is what we're trying to do in this question, I bet I've separated the variables incorrectly. You would do Vb over root 2, which would correspond to 1 over root 2, or D. Now, a force of 200 newtons is required to keep an object from sliding at a constant speed of 2 meters per second. Across the floor. and how much power is being expended to maintain this motion. All right, so what our formula is for power is work over time, right? So in other words, you can use force times distance for our work over the time, which gives us force times speed, or force times velocity, but in this case it's speed. So force times speed, where your force is 200 and your speed is equal to 2 meters per second, you would then get 400 watts as your answer. And let's check if we're all correct. We are all correct. Alright, now let's get started with rotational motion and centripetal force. This includes gravity as well, so just keep that in mind. Alright, so first I'll just explain a few concepts surrounding centripetal force. So let's say you have this circle, and you have your center here, and you have an object revolving around the circle. Now, the force of which the object is being pulled to the center is equal to m times v squared over r, where your v is the tangential velocity. Right, so in this case, the tangential velocity will be facing this way, and you want to calculate that velocity, plug that into here, square that, multiply it by the mass, and divide it by the radius, this radius over here. So that's pretty much the premise of this entire unit, and you have to remember that for gravity, your formula is g times m1 times m2 over r squared. So where your g is your gravitation constant, and we will be going more in depth into that as we go on with these questions. So let's take a look at number 1. So we have a 60 centimeter rope that is tied to the handle of a bucket, which is then whirled in a vertical circle. The mass of the bucket is 3 kilograms. Alright, so we have this, and it says that the lowest point in its path, the tension in the rope is 50 newtons. So, in other words, so we have this 60 centimeter rope, so our radius is 60 centimeters. And now for tension, your tension, right, is the force being put on the string. In this case, the forces being put on the string are mg, your weight downward, plus your centripetal force, which is mv squared over r. So we know that 50 is equal to 3 times 10 plus 3 times v squared over our r in meters. So if you want to convert 60 centimeters to meters, we just divide it by 100, you get 0.6. So you have this is your equation. Now we want to find v squared. So in this case, we can just simplify that to get this. And 3 over 0.6 is equal to 5, so we'll just label that as 5v squared. So then you would have 20 is equal to 5v squared if you move 30 to the other side. Then you'll have v squared is going to be equal to 4, and then you can easily figure out that v, your velocity, is going to be equal to 2 meters per second. Or actually, not your velocity, your speed is equal to 2 meters per second, because we don't know what direction it's traveling in. We are not given a direction, so we're only given the magnitude. Now let's move on to the next question. Alright, so a 60 centimeter rope is tied to the handle of a bucket, which is then whirled into a vertical circle. Alright, once again, we have something similar. Alright, so What is the critical speed below which the rope would become slack when the bucket reaches the highest point in the circle? Now this isn't a common question by any means, but we'll just do it. So when they say become slack, they're asking you when the motion gets to its highest point up here, we don't want the tension to be equal to 0. So in this case, our tension is equal to mv squared over r minus mg, because your mg is pushing down, right? It is pointing toward the circle. Your gravitational pull is being pulled down toward the circle, and your tension is the force that is being pulled away from the circle, right? So tension is the force of a string that is being pulled away from an object, right? So in this case, your string's base, I guess you could call it, is over here. And in order to increase the tension, you want more upward force, but in this case, gravity is acting downward, so you want to subtract mg. So we want mv squared over r minus mg to be greater than 0. So we want mv squared over r to be greater than mg if we move mg to the other side. Now we can cancel out the m's, and we get v squared over r must be greater than g. And we know that our r is 0.6 once again, so we can move this over here. V squared over 0.6 must be greater than 10. You multiply 0.6 to both sides of the equation, and you get v squared must be greater than 6. And now we can take the square root of 6, which would be somewhere around 2.4, which is one of our choices. So v must be greater than around 2.4. And we know that our answer is now C. Alright, so an object moves at a constant speed around a circular path of radius r at a rate of 1 revolution per second. What is its acceleration? So with a radius r and at 1 revolution per second means that we are circling this entire circle at 1 revolution per second, right? So from here, 1 second later, you will go around the entire circle, right? And you would end back at your original point each second. So we will want to find the circumference for this circle, and we know that the circumference of a circle is equal to 2 pi r. So we're traveling this distance in 1 second, so that is equal to our speed, right? Now we're going to use speed in terms of instead of velocity here, because we do not know what our direction is. So our force is equal to mv squared over r because we are traveling at a constant speed. And now we're trying to find the acceleration. So because we are given the force, or actually because we are solving for the force here, force is equal to ma. So we can set your centripetal force equal to mass times acceleration. Now from here we can cancel out the m's, and we get v squared over r is equal to a. And we know that our v, or speed actually, is equal to 2 pi r per second, right? 2 pi r meters per second. So we would get 2 pi r, the entire thing squared, over r should be equal to our acceleration. Now if we were to work this out, we get 4 pi squared r squared over r, and this r cancels out. So we get 4 pi squared r, which corresponds to choice D. Now we'll take a look at number 4. Right, now let's go to number 5 actually, because number 4 is based on torque, and we have not learned that yet. that will be something that we will be covering next semester. So in the figure above, what is the torque about the pendulum suspension point produced by the weight over the weight of the bob? Okay, this is another torque question. Sorry about that. All right. And I believe this is also out of the scope of this unit. So let's go down to number 7. All right, so we have to keep in mind that 4, 5, and 6 are not solvable when we are checking our answers. All right, so number 7. If the distance between two particles is double, then the gravitational force between them is... All right, so what we have here is two particles and at a distance of, let's call it r, and we know that, let's write this down, gm1 m2 over r squared is equal to our gravitation force, or our gravitational force. So over here, our r is, so our r squared is what's doubling, or r is what's doubling. So in other words, let's label d1 equal to 2r, or sorry, d1 is equal to 1r, and d2 is going to be equal to 2r. So now we have to find the gravitational force between them and compare them. So for the first one, for d1, we'll just use r squared. Now this compared to gm1 m2. Now we have to square this entire portion. So that would be 4 times r squared in our denominator over here. Now if you increase if you increase the distance between them, that means your denominator increases, meaning your force decreases. So we can cancel these out, and what we can do is actually we can divide these two, right? So we can get the distance 1 over distance 2, or actually we should rather go with this option. We should go this divided by this. So we would get g m1 m2 over 4r squared. Right now we'll do the formula for dividing two fractions, which is to multiply the reciprocal, the reciprocal being r squared over g m1 m2. Now obviously g m1 m2 cancels out for both terms, so we would get, and also r squared cancels out, so we would get 1 over 4, which corresponds to decreasing by a factor of 4, which is a. Now let's take a look at number 8. At the surface of the Earth, an object of mass m has weight w. Alright, so if this is transported to an altitude that is twice the radius of the Earth, then at the new location, right, so we know that gm1 m2 over r squared is our original, and now we want to go twice the radius of the Earth upward. Alright, so this is 1r from the center of the Earth. Okay, now this is 1r again, and we want to go another r, so we are tripling the radius. Alright, so now by tripling the radius, we can set d1 equal to distance 1 right at the surface of the Earth, right here. And we'll set distance 2 equal to 3r. Now we can plug it in, and for the first one, right? With d1 we get g m1 m2 over r squared versus the next one, which is g m1 m2 over 3r squared, which is equal to 9r, 3r squared, as in 3r, all of that squared, right? Which would then be that. Now, we would want to divide your second force by your first force, and you would get g m1 m2, basically the same thing we did in the last question, g m1 m2 over 9r squared times r squared, because we're taking the reciprocal, over g m1 m2. So we can cancel this out, cancel the r's out, so we'd get 1 over 9 as our new relative weight. So with this, the only choice that matches is this right here. So D should be our answer, but let's check the other part of the question, which is its mass is m, and we know that mass does not change at all. There is no information that makes us change our mass here, so D is our answer. Now let's take a look at number 9. A moon of mass m orbits a planet of mass 100 m. Let the strength of the gravitational force exerted by the planet on the moon be denoted by F1, and let the strength of the gravitational force exerted by the moon on the planet be F2. Now this is an action-reaction pair, as we were discussing in the other part of the video during the forces unit, right? So if we have a planet and a moon, this moon is being attracted to the Earth, or not the Earth, the planet, but the planet is also being attracted to the moon at the same force, but because the mass is much larger, right? This is 100 m. The acceleration, or the force toward force toward the moon of the planet is not noticeable, and it does not get affected too much. So because this is an action-reaction pair, our answer is C. They are going to be equal. That is Newton's third law. Every action must have an equal and opposite reaction. Now let's take a look at number 10. The dwarf planet Pluto has 1 over 500 times the mass and 1/15 the radius of the Earth. So what is the value of g in meters per second squared on the surface of Pluto? Alright, so use g1 m2 over r squared. Now 1/15 the radius. Alright, so we'll label d1, right, for Earth as r, and we'll label m1, which is supposed to be our planets or whatever the gravitational or origin is, I guess. We label that as m1, and this is the Earth's mass. And we'll label mb or mp for Pluto's mass. It's going to be 1/15 times m1. Or sorry, this is 1/500th times m1. Earth mass. So now we know that our distance to is equal to 1/15th r. So now we'll write our equation. We have g times 1 over 500 m1 m2 over 1 over 15, sorry, I forgot to label this, times d1 times r squared, right? Because we're replacing d1 with r and we're replacing m1 with that. So we get, on this side, we get g m1 m2 over r squared. Now we have to multiply it. Now we have to multiply this by, oh sorry, this is supposed to be 1 over 15 r squared, right? Because 1 over 15 r, right, is supposed to be our distance to, or d2, and we want to square that entire portion. So we would get 225 over 500. Now the reason for that being, if you were to have this multiplied out, you would get 1 over 225 r squared. Now if you want to move this, if we want to take out the 1 overs, right, the reciprocal of 500 on the numerator would equal 500 on the denominator, and the reciprocal of 225 on the denominator would equate to 225 on the numerator through algebra, right? Now you want to divide this entire portion by this right here, which is the Earth's force. So you would get that, and we can cancel out this entire portion over here. So now we have your information. So we have 225 over 500, which is equal to the proportion of the, we have the proportion of Pluto's gravity compared to the Earth's gravity. Now, this is a proportion system, so we have to multiply by the Earth's gravity. Now, the Earth's gravity is 10, right? We're using 10. It's more exact at 9.8. So now we have 50 here, and we cancel out this. And 225 over 50 corresponds to choice D. So we'll check that. All right, a satellite is currently orbiting Earth in a circular orbit of radius r. Its kinetic energy is K1. Now, if the satellite is moved and enters a new circular orbit of radius 2r, what will be its kinetic energy? All right, so what we can do is we can use your g m1 m2 over r squared. Now this is equal to your centripetal force, right? So your centripetal force, as we know, has this as its formula, mv squared over r. But the reason it's m2 over here is because m2, you gotta remember, right? So you have this, and we have this planet over here, or this moon or something. This is m1, and this is m2. The object orbiting is m2. The object that is being orbited is m1, and mv squared over r, the m in that equation, is equal to the orbiting object. So these two do relate to each other. So we can set g m1 over r squared equal to v squared over r. And now we know that our v squared is going to be equal to g m1 over r, because you're going to have r squared over here and r over here. If you multiply r to the other side, this r, and then you would cancel this and the exponent on this one out, so you would get gm1 over r for your v squared. Now we won't be taking the square root because kinetic energy is equal to 1/2 m times v squared. So in this case, our kinetic energy will be equal to 1/2 times m2 this is, times this over here, your g m1 over r. So essentially what we can do now is actually, we'll simplify this. You'll get g m1 m2 over 2r. Right, so now we have established a relationship, an inversely proportional relationship between kinetic energy and your radius, assuming that g m1 and m2 remain constant, right? And we are assuming that they are remaining constant, so your kinetic energy, right, your k is inversely proportional to r, or to r. So as r increases by a factor of 2, your k will decrease by a factor of 2. And, right, so if your r multiplies by 2, your k divides by 2, and that corresponds to choice B, which is our answer. Now, a moon of Jupiter has a nearly circular orbit of radius r and an orbit period of t. Which of the following expressions gives the mass of Jupiter? All right. So it is a nearly circular orbit, so we will be using centripetal motion, and an orbital period of t with the radius of r. So now what we can do is we can find the velocity, right? So if we have this, right, and we have Jupiter here, and we have the moon of Jupiter. Actually, I'll take out that circle. We have the moons of Jupiter orbiting around it. And we have this radius of r. So we're trying to find distance over time, which gives you your velocity. Now we are given the orbital period of t, so we'll have distance over t is equal to v. Now we need to find the distance that it travels. Now, with the distance that it travels, we can just use the circumference. Circumference is equal to 2 pi times r. So our velocity is equal to 2 pi r over t. Now, we can use the centripetal force equaling this, mv squared, where v is equal to 2 pi r over t, mv squared over r, and this is also going to be equal to the gravitational force, which is g m1 m2 over r squared. Now, I forgot to mention that this m that we are using over here is equal to m2 because we are once again using this mass right here for our centripetal motion force. So we can cancel this m out and replace this with m2, and we can cancel out the m2, and we're doing something very similar to what we were doing in the previous equation. So now we'll have v squared over r, v squared over r is equal to g m1 over r squared. Now from here we want to separate the we want to separate the m1 because that's where we're trying to find the mass of Jupiter, which is m1. So we'll have m1, right, and now we can multiply this to the numerator and then divide g. So we will have v squared times r squared over r times g. And now we can cancel this exponent out, take out this. So we'll have m1 is going to be equal to, I'll put this down here, m1 is going to be equal to v squared r over g. But now we found out v over here, we'll replace v by that. So let's find out the v squared over here. V squared will be equal to 4 pi squared times r squared over t squared. Now, if we just replace v squared with that in this equation, right, we will have 4 pi squared r squared over t squared times r over g. So then we can simplify this to be equal to 4 pi squared r cubed, right? Multiplying r squared and r yields you r cubed over t squared times g. Right, now the one that this corresponds to looks like it's going to be equal to d. Yes, d is our answer. Now we will move on to number 13. Two large bodies of mass m and mass 4m are separated by a distance of r. At what distance is body A along the line joining the bodies with the gravitational force on an object be equal to 0? Alright, so we will have object B, or body B, then we'll have body A. And we know that the distance between these two objects, these two bodies is equal to r. And we have an object in the middle of them. And now we'll label this, label this object O. Now we'll label the distance from A to O as D, and thereby making the distance from O to B R minus D. Now we want the net gravitational force, right, on the object to be equal to 0. So we have two forces acting upon it, right? GB pulling this way and GA pulling the other way. Gravitation of force of body B and body A. Now they will be deferring, so you want GB minus GA to be equal to 0. You can move GA to the other side to get GB equaling GA. I'll put the A a bit smaller. So now we can use our gravitational forces formula. So we get Gm1m2 over r squared. Or actually, let's replace m1, right? Well, this is the gravitational force of body B. So body B's m1 is going to be equal to 4. So we will label this as G times 4m, right? So we'll label this as 4m. And now the distance to this object, to object O, is r minus d. So we will have r minus d squared. Now we'll set that equal to g times regular m, because the mass of body A is m, times m2 over regular d squared. So now we will be able to cancel out m squared, gm times m2, and on this side we will be able to do the same. So you get 4 over r minus d squared equaling 1 over d squared, right? And I forgot to put the parentheses here. That is very important going forward. Now we can multiply 4 on both sides, or actually we can use cross multiplication for this. That will make it a lot easier. So we get 4d squared is equal to r minus d squared. And now let's save space and move this over here. Right, so 4d squared equaling r minus d squared. Now we can move d squared, we can move this down here to this denominator. So we get 4 is going to be equal to r minus d squared over d squared. Now we can take the square root of both sides. We get r minus d over d is equal to 2. And with that, we can then get r minus d is equal to 2d, right? And we will get 3d is equal to r. I know this is getting a bit hard to read, but just bear with me. So now we can solve for d as equaling r over 3, right, so 3d is equal to r. We'll move this up here now. 3d equaling r. So if we want to separate the d's, we get r over 3 as our final answer. So that is equal to d. And now we will move on to question 14. We're looking at the top view of a planet orbiting the sun in a clockwise direction. Which of the following correctly represents the velocity, force, and acceleration acting on the planet. So we know that centripetal force always heads toward the center. That is a property of centripetal force, right? So we have tension that heads toward the center of an object. We have gravity that heads toward the center of the system, right? We have gravity that goes toward mass 1, which is the center. So in this case, your force at point P will be pointing toward the sun. And your force is also in the same direction as your acceleration. So both your F and your your F and your A should be pointing toward the center. Right, so we can cancel out C and A from that. Now our choices are between B and D. Now our velocity, because we are moving in a clockwise direction, and by this diagram, your inertia is still moving downward, or from our perspective, downward. So yeah, you are still heading, right, at this particular moment, you are still heading downward. You're heading at a tangential path to the circle. And that corresponds to choice B. Now question 15. An object of mass m is traveling at a constant speed v in a circular path of radius r. How much work is done by the centripetal force during 1/2 of a revolution? Alright, so we have, so the centripetal force we can calculate. They give us all the variables. It's mv squared over r. Alright, now this is equal to our force, and we want to find the work done during 1/2 of a revolution. So we have our circle here, and we are traveling from this side to this side. So we want to find the circumference of the semicircle that is created by this path. So the formula for the circumference of our semicircle is equal to 2 pi r over 2, because what we're doing is taking the full circle's circumference and dividing that by 1/2, or dividing that by 2, because you're only taking half of the circle. So now we have pi r as our distance that we are traveling. Now we do know that work is equal to force times distance from our energy unit. So we will have our force here of mv squared over r times pi r, which is our distance, right? Our circumference of the semicircle. Now we can cancel out this r and this r to get mv squared times pi, and that corresponds to. Now based off of that, this should be correct, right? Right, if you're using force times distance, that should be correct. No, that is completely incorrect, because your force must be parallel to your distance, right? So in order to use your force times distance, you need to find the component of your force that is parallel to your distance traveled. Must be parallel. And this sign is parallel to distance. But in this case, right, if you're looking at any object with centripetal motion, your force, as I mentioned earlier, is always pointed inward, right? But your object's motion is going to be on a tangential path to the circle. And on a tangential path, that means it is completely perpendicular to the force, right? So your force is perpendicular to the distance. Now, perpendicular is basically the opposite of parallel. That's as far as you can get away from being parallel, meaning that there is no component of F that is parallel to D. So, no component of F is parallel to D. So you will have a force of 0, which is parallel to D, times D traveled, which gives you 0 as your answer. So it is not A, it should be B. So Now, if you check our answers, we do get 4, 5, and 6 wrong because those are torque, and we have not learned that yet. We will be covering that next semester. So now let's submit. These 3 are wrong. Everything else is correct. And we are now done with our review for centripetal motion.